This is a lecture on valence bond theory. Valence bond theory is an alternate to molecular orbital theory and attempts to explain what happens with the orbitals when making a covalent bond. All right, so prior to valence bond theory and molecular orbital theory, we simply had Lewis theory, which is very valuable, you'd probably agree. That's, of course, when we just have the elemental symbol with the dots around it representing the number of valence electrons. It's very handy for getting a first rough approximation of how many bonds an atom can make. But it doesn't explain some of the specifics, the specific bond angles we view. It doesn't, if you deal only with the atomic orbitals of S, P, and D, they're right here. It doesn't explain the molecular shapes we observe, the tetrahedral and trigonal bipyramidal. And so Linus Pauling was one of the key contributors to the valence bond theory. And he focused in, at least initially, on how we could get the shapes that we observe from the atomic orbitals. And he decided, for a variety of legitimate reasons, that he would theorize that the atomic orbitals, when they overlapped to make a bond, formed hybrid orbitals. And so what do I mean by hybrid? So hybrid just in the dictionary means a blend of things, right? So, for example, let's look at an S atomic orbital and a couple of P atomic orbitals and blend them together. And then what we get from blending those together, and you could check this, not you personally, but it's not just random shapes. Remember that orbitals are wave functions. And so when you blend the wave functions mathematically, you get, in this case, some sp2 orbitals, okay? And this figure just puts all three of them together. But you can see from this figure that if you put three of these hybrid orbitals together, it explains our trigonal planar shape. And so you'll see as we go through all the slides that we can actually nicely explain all of the shapes we observe using these hybrid orbitals. So some rules in making hybrid orbitals. Of course, every atom that hybridizes has available to it an s orbital. Remember, there's only one s orbital and an s sublevel. And then a close in energy p sublevel. Of course, every p sublevel has three available orbitals. So we will be beginning to talk about hybridization with s and p orbitals. So if we hybridize the s orbital with all three p orbitals, so that's shown in the diagram here, okay? Anytime we combined atomic orbitals in any way to get molecular orbitals, we must conserve the number of orbitals. So if we start with 4 atomic orbitals, as we did here, we must end up with 4 hybrid or 4 molecular orbitals. So when you blend an S and a P, you get these funky kind of uneven lobule shapes, and you have to get 4 of them. 4 of the hybrid orbitals because you started with 4 atomic orbitals. Now what's nice is these 4 hybrid orbitals are of equal energy, and that's always the case with the hybrid orbitals. We get however many orbitals we started with, but all of equal energy, and you'll see later that that explains a few things also. So to give you just a little bit of theory about why Linus Pauling came up with the idea of hybridization is, for example, if you look at the orbital configuration for carbon, 2s2, 2p2, it looks like carbon will only make 2 bonds, trying to pair up these 2 electrons. But we know, in fact, that carbon makes 4 bonds, okay? So valence bond theory theorizes that an electron from the S sublevel is promoted to the nearby P sublevel, so that you would then get my dog wants to play fetch. Sorry about that. So that you end up now with 4 unpaired electrons. So you can start to envision, okay, well, if this happened, I can see maybe why carbon wants to make 4 bonds. It has 4 unpaired electrons. However, it had been observed that when carbon makes 4 bonds, let's say with 4 hydrogen atoms, all 4 of those bonds are equivalent. So leaving it unhybridized, you would expect one of the bonds it makes using this 2s orbital to be different in some way from the 3 bonds made from the P. And they weren't. They were all equivalent. So Pauling came up with the idea, let's hybridize these so that we get the same number of unpaired electrons, but in equal energy hybrid orbitals. And the hybrid orbitals are named. The name tells you exactly how many of each type of atomic orbital they came from. So you can see that sp3 has 1 s orbital and it has 3 p orbitals. Okay? So that's what it was made from. So that sp3 hybridization also explains the shape we see for carbon making 4 bonds, which is a tetrahedral shape. And what they've done here is combine all 4 hybrid orbitals that are made together, and they can combine them in a tetrahedral shape. So hybridization theory seemed to be working real well for shapes and energies of bonds. So this is just a better diagram showing the individual sp3 hybrids being made, and then combining them together to make the tetrahedral shape. All right, so what you need to remember, what will likely show up on a test, is any atom that is sp3 hybridized doesn't just have to be carbon. It could be nitrogen, sulfur, oxygen, lots of things. Okay, anything that is sp3 hybridized will have tetrahedral geometry, and I'm hoping that you remember tetrahedral geometry is associated with 109.5 angles. And I'll repeat this a couple of times, but if you remember molecular shapes and counting electron domains, it turns out that every electron domain needs a hybrid orbital, okay? So another way of saying that is all single bonds and lone pairs of electrons need a hybrid orbital. All right, so keep that. All right, so remember that we are starting, every atom that hybridizes has available an S sublevel and a P sublevel, the P sublevel with 3 orbitals and the S with 1. Now we can either combine all of them to make sp3, or what if we only use 2 out of the 3 available p orbitals? What would we call that? Well, remember that the name of the hybrid is from how many of each type of orbital. So we have 1 s and we have 2 p's, okay? So if we only use 2 of the available 3, we have made sp2 hybridization. Since we started with 3 atomic orbitals, an s and 2 p's, we have to end up with 3 hybrid orbitals. So we are going to have 3 sp2 hybrids available after the hybridization. They'll all be equivalent to each other. And so if you arrange 3 hybrid orbitals so that they're as far away from each other as possible, remember they're going to have electrons in them, so they still will repel each other. Now, if you arrange 3 sp2 orbitals together, putting them as far away from each other as possible, then you get the trigonal planar geometry, okay, with 120-degree angles. And so what I want you to remember about sp2 hybridization is that It is always associated with trigonal planar electron domain and 120-degree bond angles. All right, I'm going to pause here a minute because you may have noticed when we have sp2 hybrids that there's a leftover p orbital that hasn't been used to make hybrids. And you will see as we go on that these leftover p orbitals are used to make pi bonds. So I want to explain the two types of bonds. They are sigma and pi. And so a sigma bond is head-to-head overlap. Okay, direct overlap of two atomic orbitals or two hybrid orbitals, whatever. Those are the strongest type of bonds. All single bonds are sigma bonds. Okay. Now, side-by-side overlap of p orbitals, so that's like these, they can still overlap and interact, but it's not as strong of an interaction. Those are pi bonds. Okay. So it turns out that double bonds and triple bonds are made up of sigma bonds and pi bonds. Okay, so but keep in mind that it is the p orbitals, the lone p orbitals, that are used to make pi bonds. So let's look at formaldehyde, for example. What you're going to be doing is you know how to count electron domains. So formaldehyde has 3 electron domains, and I don't know if you remember me saying that every electron domain needs a hybrid orbital. So you have 3 electron domains, which means you need 3 hybrid orbitals, okay? And which means you have to start with 3 atomic orbitals. So you need to start with s and 2 p's. So we will need sp2 hybrids. That's what these purple things are meant to demonstrate, is the sp2 hybrids made on carbon. Now, of course, since you started with 3 atomic orbitals and s and 2 p's, you get 3 hybrids, 3 sp2 hybrids, and you have a p orbital left over, okay? So the p orbital left over is going to form a pi bond, a double bond with oxygen. So look back at the Lewis structure, and I've got this, I think, on the next page too. But anytime you have a double bond, one of the bonds is a sigma bond, head-to-head overlap, and one of the bonds in a double bond is a pi bond. And so anytime you have a double bond, only one double bond, you are going to need sp2 hybridization with 1 p orbital left over to make that pi bond. Now, let's talk about sp hybridization. So what if we use the s orbital and only one of the 3 p orbitals? So let's say we do this. So we started with 2 atomic orbitals, which means we will get two hybrid orbitals, and those hybrid orbitals will be called sp hybrids, made from 1 s and 1 p. Okay, so here are the 2 hybrids. When you arrange them together, you get a linear shape. And what do you have left over? Okay, when you do sp hybridization, you have 2 p orbitals that are left over. Every p orbital left over can form a pi bond. So that means if you have 2 p's left over, your structure must need 2 pi bonds. So let's look at some examples of atoms that are sp hybridized. Alrighty. Let me draw the Lewis structure. This is called acetylene. And it turns out that in triple bonds, one of the bonds is sigma, the head-to-head overlap, and 2 of the bonds are pi bonds, side-to-side overlap. So anytime you have a triple bond or 2 double bonds in a molecule, you need sp hybridization so that you have the p orbitals to make the 2 pi bonds. So you can kind of see the diagram here. I'm not going to ask you to draw this diagram, but sp hybridization has each carbon has 2 sp hybrids, and then they have 2 available p orbitals to make the pi bonds, or which is a triple bond in this case. All right, so what you need to remember about sp hybridization. The shape associated with sp hybridization is linear. The bond angle is 180. And I said this a few times, but just to remind you, all sigma bonds and lone pairs need a hybrid orbital. So that means when you count electron domains, okay, that is how many hybrid orbitals. So if you have 4 electron domains, you need 4 hybrid orbitals, which is sp3, right? If you have 3 electron domains, you need 3 hybrid orbitals, which means it's sp2. If you have 2 electron domains, you need sp. Now, of course, if you have sp2, you have a leftover p orbital to make a pi bond. If you have sp hybridization, you have 2 leftover p orbitals to make 2 pi bonds. All right, here is, shoot, I showed the answer, didn't I? Oh, well, I'll walk you through this one. So this is a typical question that can be asked with hybridization. What's the hybridization of the central atom in phosphorus trichloride? You have to draw a Lewis structure. If you don't do that, you're likely going to get this wrong. So how many total valence electrons? Phosphorus has 5. Each of the chlorines has 7. So we are talking about 26 valence electrons. Phosphorus is less electronegative than chlorine, plus it's the first atom. So it is a central atom. And I'm going to place single bonds to begin with, give all of the outer atoms an octet, and then check and see how many electrons I've used at this point. Anytime you make an octet, that's 8 electrons. So that's 8, 16, 24. I have 2 left over. Remember, if you have leftover electrons, they go on the central atom, which is good because phosphorus didn't have an octet. And that is your Lewis structure for phosphorus trichloride. Then you count the number of domains, 1, 2, 3, 4. So if we have 4 domains, each of those domains, and another way to think of it is each sigma bond and each lone pair, each of those domains needs a hybrid orbital. So we need 4 hybrid orbitals. And the way we get that is with sp3 hybridization, okay, which starts with 4 atomic orbitals, right? An s and all 3 p's. And we end up with 4 sp3 hybrids, which is what we need. Okay, no leftover p's, no double or triple bonds. That's cool. All right, so we're going to move on now. What about the molecules we know that have 5 domains or 6 domains? We have run out of s and p orbitals. What do? It turns out that if you have 5 domains around a central atom, one of the nearby d orbitals can hybridize with the s and p orbitals. So we end up with what we call sp3d hybridization. Now, count how many atomic orbitals did that come from? 1 s, well, I'll do this. 3 p's, okay, p, and 1 d. So we started with 5 atomic orbitals. So we have to end up with 5 hybrid orbitals. So we get 5 sp3d hybrids. Okay, 1, 2, 3, 4, 5. And so what you need to remember is that any atom that's sp3d hybridized will have trigonal bipyramidal electron geometry. Okay, this is not molecular geometry necessarily. This is the geometry that is associated with the electron domain geometry. Alrighty, and if you have 6 domains, that means you need to start with 6 atomic orbitals, which is an S, 3 Ps, and 2 Ds. Okay, that'll give you 6 domains, 6 hybrid orbitals. And so if you see sp3d2 hybridization, that is always associated with an octahedral electron domain geometry. Alrighty, so here's kind of a nice summary page of all of them. SP hybridization is when you have 2 electron domains, and the shape will always be linear. If you have 3 domains, hybridization will always be sp2, and the shape will be, electron domain shape will be trigonal planar. If you have 4 domains, tetrahedral shape and sp3 hybridization. 5 domains is sp3d and trigonal pyramidal. 6 domains is octahedral and sp3d2. So commit these to memory. Alrighty, so if you are asked to predict hybridization, this is the thought process or the steps you need to go through. Always, always, always start by drawing a Lewis structure. Then count your electron domains. And then hopefully you've memorized the chart on the previous slide so that you know what the hybridization is going to be. And here it is in list form again. Okay, 2 domains SP, 3 domains SP2. Okay. Alrighty, here's one last question for you. Match the hybridization I have on the far right with the appropriate geometry. So put the video on pause and see if you can do it without peeking back at the chart. And then I'll go over it with you. So hopefully you tried this on your own. So tetrahedrals, 4 domains. So it is sp3, because that's 4, and S and 3 Ps make 4. Linear is only 2 domains, so that is sp. Trigonal planar is 3 domains, so that's sp2. Trigonal bipyramidal is 5 domains and sp3d, and octahedral is 6 domains in sp3d2. That is it for valence bond theory. I also have a lecture on molecular orbital theory.